Okay, okay, now let's try to say about the LCR series circuit. For saying about the LCR series circuit, let's draw an inductor, a capacitor, then a resistor. Inductor will have a self-inductance of L, capacitor will have a capacitance C, resistor will have a resistance R. They are connected in series to an alternating power supply of voltage V is equal to V0 sin omega t. This is the alternating voltage, and since this is series combination, the current flowing through all the components will be same. That is, inductor will have a current I, means capacitor will also have a current I, resistor also will have same current. But in this case voltage will be different, therefore let me write VL, VC and VR. VL is the voltage across inductor, VC is the voltage across capacitor, and VR is the voltage across resistor. Then now we are going to draw the phasor diagram of that. That is, if we are drawing the phasor diagram of this particular circuit, let me draw the axis first. This is our axis, and in this axis, since current is same in all this case, we are drawing the current phasor initially. This is our current phasor, current. And we have studied that current and voltage across resistor is in phase. VR is in phase with I. We have studied it in our previous sessions. Therefore, we could draw voltage across the resistor in phase to the current. I am drawing it like this. This is on the current phasor itself, and this is VR, voltage across inductor. Then in the case of capacitor, we have learned that in capacitor the current will lead by an angle of pi by 2. That means in the case of capacitor, voltage will lag by an angle of pi by 2. Since voltage is lagging by an angle of pi by 2, we have to draw the voltage over here. This is our voltage across capacitor, VC. Then from our previous knowledge, we have learned that in an inductor, the current will be lagging. That means voltage will be leading. Current will be lagging by an angle of pi by 2. As a result, voltage will lead by an angle of pi by 2. Therefore, we have to draw the voltage leading current by an angle of pi by 2. Therefore, I am drawing voltage across inductor like this. You could clearly see the length of VL and VC is not same. In this case, I am having a situation where VL is greater than VC. Should it be always like this? No. But it could be like this also. Therefore, now we are taking a situation where voltage across inductor is greater than voltage across capacitor. If this is the situation, means let's initially solve the vector sum of VL and VC. If VL is like this, VC is like this, then what is the net sum of VL and VC? It will it be in the direction of VC or in the direction of VL? It will be definitely in the direction of VL. And you have learned that if this is a, let's assume that 6 Newton force, and if this is a 2 Newton force, then the answer of this will be in this direction, and it will be 6 minus 2, that is 6 minus 2, that is equal to 4. Likewise, VL and VC will have an answer in the direction of VL itself, and this will be VL minus VC. VL minus VC. Then we can forget about this VC and VL. Instead of this VC and VL, we are having VL minus VC. VL minus VC and VR, we have to add the vector sum. For that also, if there is a vector A like this, and if there is a vector B like this, according to our parallelogram law of vector addition, we could construct a parallelogram like this, and this should be the resultant. We have learned it in our +1 sessions and all. And if this angle is theta, the resultant's formula will be root of a square plus b square plus 2ab cos theta. This is from our previous session, and if we are using this logic over here, VL minus VC and VR, the vector sum will be, we will have to construct a parallelogram like this, and the vector sum will be in this direction, and this is the resulting voltage. The sum, vector sum of VR, VC and VL will be in this direction, V. And what's the total current? The total current is I, it's over here. The total voltage is V, this is over here. The voltage and current, it will make an angle phi. Phi is the phase difference between current and voltage. And from this diagram, it is clear that the voltage is leading, or in other words, current is lagging. Current is lagging by an angle of phi. Therefore, if V is equal to V0 sin omega t is the expression for this voltage, from this phasor diagram, it is clear that current is lagging. Therefore, I could write I is equal to I0 sin omega t minus phi. Current is lagging. And from this phasor diagram, if we are trying to find out the mathematical expression for resulting voltage, we could say if this is A and this is B, R is equal to a formula like this. Then what is V is equal to? It should be the vector sum of these two by comparing this parallelogram with this parallelogram. You could say V is equal to root of, instead of A square, it is VL minus VC the whole square plus VR square plus, there is a 2AB cos theta. In this case, theta is the angle between VR and VL minus VC. They are perpendicular to each other. Therefore, the theta value in this will be 90. What is cos 90? The value of cos 90 is 0. Therefore, this is enough. The next term will become 0 since theta is 90 degree and cos 90 is equal to 0. Then, what is VR? According to Ohm's law, voltage is equal to current into resistance. Therefore, VR is equal to current across this resistor into resistance. Then, what is VL? VL is voltage across inductor. If you are using that same logic, it should be current into resistance. I didn't say current into inductance, I've said current into resistance. The inductor will offer an obstruction of XL. We have learned that the total obstruction offered by inductor to the flow of current, it is inductive reactance XL. Therefore, VL can be written as I into XL. Who is XL? XL is inductive reactance. And in this case, or if I am writing VC, what is VC? VC is I into obstruction of capacitor. capacitor will offer an obstruction of Xc, capacitive reactance. Therefore, Vc will be I into Xc. Then we could rewrite this equation for V as V is equal to root of IXL minus IXC the whole square plus IR the whole square, from which we could take the I square common out, and if it is taken out of the root, I root of XL minus XC the whole square plus R square V. Then what should be V by I? Let me write it over here. Therefore, V by I is equal to root of XL minus XC the whole square plus R square. And V by I is total voltage divided by total current. It is total obstruction. Total obstruction in this case, it is called as impedance. Impedance Z. What is that? Z is impedance. Impedance is equal to root of XL minus XC the whole square plus R square. This is the formula for impedance of LCR circuit. What did we say? We now discussed about the LCR series circuit and what is the phasor diagram of LCR series circuit if VL is greater than VC. If VL is greater than VC, the current is lagging by an angle of phi. Then the resulting voltage is like this. The total obstruction offered by the circuit will be the root of XL minus XC the whole square plus R square. We could use this formula both if VL is greater than VC or VC is greater than VL. Any case, the formula it could be used like this. Or if anyone is asking us, if we are writing XC minus XL, will it be technically wrong? No. XL minus XC the whole square is equal to XC minus XL the whole square. Since there is a square, the negative sign will vanish. Therefore, this is the formula. And you have to remember that if VC is greater than VL, this won't be the phasor diagram. The voltage will be downwards and the current will lead. Therefore, it will become I is equal to I0 sin omega t plus phi. That is, if VC is greater than VL, it will become plus phi, or the current will lead by an angle phi.